Send me the link, no? It's on live? Okay, fine. Good evening, everyone. So, welcome to the contact hour for week 7. As usual, I will request you to type in your questions and then I will try to answer it one by one. And if there are not many questions, I will actually start, discussing the solutions to the assignment problems. So please type in your questions. Mahesh, any questions in the chat? I am not able to see. Can you hear me? It's okay, no? Yeah. Okay, fine. What we wanted to, what we did to this week was about detectors. So we talked about responsivity. Uh, we talked about quantum efficiency. Eta. After that, we talked about relation between but in the YouTube, I'm not able to see, so I don't know what's going on. Okay. Yeah. So we talked about responsivity, quantum efficiency. We talked about why you need this PN junction, and short noise and thermal noise, and mostly ignored source of noise, which is the noise due to the dark current in the receiver. Uh, Now, conceptually, how do you understand these noise? Let's say I'm transmitting. So all this entire week we did transmission for NRZ. Okay. So the entire week 7 was for NRZ. Okay. We'll talk about coherent transmission. Sorry, is that Mahesh? Is there a problem because I'm getting a message that the voice is not continuous? Okay, and this is important to keep remembering because some of these results will look different, or you will have to. I mean, the results won't be the formulae or the concepts won't be different, but if it is a coherent system, we need to apply them differently. So the other thing we talked about noise, and to get you understand the concept of noise, what we can how do you visualize this? So let's say you're transmitting an on-off keyed signal, which is between 0 level and 1 level. At the receiver, what you will receive is some noisy values corresponding to 0 and other noisy values corresponding to 1. This is what you would receive. And how do we quantify the noise? We quantify the noise by plotting the histogram of the noise, which means you calculate, at every time instant, you discretize, find out what are the values of the current at all instants of time, and you plot the histogram of that current. How do you do that? You basically count the number of instances at which you got this value, number of instances you got this value, number of instances you got this value, and that number of instances is what is plotted along the mean. So you will really see that corresponding to close to the mean, you will have a larger number of occurrences of this, the average value, and it will start falling off. Similarly, you will plot the histogram corresponding to the loop. Now, the noise is quantified as the variance of this histogram, right? Because noise is not really something that is predictable, it is statistical. So how you will quantify noise is through the variance of the histogram. And for short noise, we define the variance of the histogram as 2q, where q is a charge of the electron, photocurrent, plus current. This part is the noise power spectral density, and times delta F, where delta F is the bandwidth of the detector. Now, we used either B or delta F to represent the bandwidth. Now, thermal noise, sigma T square, is the variance of thermal noise is 4kT by R. Noise figure of the electronic amplifier you have used times delta F, where ID is the dark current. This is not quantified. Typically, if the signal strength is large, we typically say the ID is almost 0 corresponding to the signal strength. So these were the key things that you learned in the previous week about the noise properties of the receiver. The other thing you learned was the distinction between Homodyne versus direct detection versus Homodyne detection versus heterodyne detection. Where in heterodyne detection, you basically use a local oscillator to push your receiver to receive your signals in the short noise regime. So depending on which source of noise is dominating, you classify the detector operation to short noise dominated regime of operation and thermal noise dominated regime of operation. And that classification is very simple because, the photocurrent that you got here, the photocurrent you got here is actually responsivity times increases with power. Larger is your power, larger is your short noise, whereas thermal noise is independent of the power, which means that depending on the operating power, you can decide whether short noise is dominating or thermal noise is dominating. And you get some peculiar dominated regime because that is what is called as a quantum limit in noise, as we had seen in the class. So in order to push the operation to the short noise dominated regime, we use either homodyne or heterodyne detection, basically coherent detection. And in case of homodyne or heterodyne detection, what you will have is you will have the receiver, you will have the signal that you want to receive, and in addition, you will have a local oscillator, which is another laser, which is falling on the receiver. and what you are detecting is the beat between the signal and the local oscillator. So your received signal is actually, received signal of interest is 2RD. So this is something again we derived in class, so I'm not going to re-derive. So this is 2RD square root of PS PLO, where PLO is the local oscillator power, cosine of, okay, let me write this again. The received signal of interest is twice the responsivity times root of signal power times the local oscillator power times cosine of delta omega IF, or just omega IF, which is the IF frequency. Now, what is this omega IFT plus delta phi? And this delta, or this omega IF is nothing but, if omega S is the center frequency of the signal, omega LO is the center frequency of the local oscillator, omega IF is actually the difference between omega S and omega LO. And delta phi is actually the phase difference between the two. And in homodyne detection, this delta omega IF, this part, this actually becomes equal to 0 in homodyne case. And in heterodyne case, you have that frequency non-zero. So later in probably week 10 or something, we will talk more about this homodyne, heterodyne detection and coherent detection and so on. Right now, we will confine our attention to how to calculate the signal to noise ratio of homodyne detection and the heterodyne detection. And we have done that for both this, and we have derived that the SNR is, in one case, is eta times PS divided by h nu times delta F, where delta F is the bandwidth of the detector in heterodyne case. Whereas in SNR for homodyne case, you get more power in homodyne because there is no sinusoid here in homodyne, because omega IF is 0, there's no sinusoid. So you will get, if you have heterodyne, when you average this part, this cosine part, this averages to half. So the power, net power that you will receive in heterodyne, average power you will receive in heterodyne system is actually half that of the homodyne system. So you will get a benefit of that in homodyne in terms of SNR, this divided by delta F. So this is what constituted the week. Now, if you have any questions on this, please let me know. If not, I will start looking at solving the tutorial assignment problems. So let's look at assignment questions. So the first question is ratio of SNRs of homodyne detection to the direct detection in short noise limit, right? So I just said that the signal of interest is this for homodyne detection. So the power, the signal power is the signal power would be 2 So whenever you calculate SNR is equal to signal power divided by noise power. Just give me a minute. I'm just trying to take out the question exactly. Meantime, you please ask your questions if you have any. Yeah. So SNR, we always calculate electrical SNR, right? So electrical SNR is electrical signal power divided by electrical noise power. And we should also remember, whenever you calculate this signal power, do you take peak power or average power? So this I told in the class also, that you have to mention. If it is not mentioned, it is typically SNR average, right? So SNR for a direct detection receiver is actually signal power divided by average signal power, which is current I square divided by resistance, right? The photocurrent square by resistance. And noise power. Why am I interested in noise power? Signal power in the electrical domain, because the noise is always defined as noise in the current. So the numerator should also be in terms of electrical quantity. So this is electrical power divided by noise power. Is we already said that it is short noise limited regime, and the variance, which is square of the current. So it's the square of the noise power, that is noise current, which is already corresponding to power. So this is sigma S square times the resistance. This will be electrical signal power, and this would be noise power. And of course, this R cancels because it is the same impedance. So you will get SNR as IP square divided by sigma S square. Now, what is IP? It is it's a photocurrent. And what is photocurrent? We already said that if a power P falls on the detector, it gives you a current I, which is the I detector current is RD times Pin. If Pin is the power that is falling. So this is RD square. And since I'm talking about average power, I will say RD square Pn square divided by what is short noise? Short noise is 2Q times I, which is RD times Pn. And there should be a bandwidth, so that is delta F. Right? So which means that your SNR for a direct detection system would be RD square Pn. Pn cancels, so you will have divided by 2Q times RD times delta F. This is for a Homodyne detector. Now for a coherent detector, what is different? The signal of interest. The signal of interest is not really just PS. The signal of the photocurrent in this case will be twice RD. Of course, I'm taking Homodyne case. We just saw it here. It is twice RD square root of PS PLO. Twice RD root of PS. If I take the average power, it is PS bar of which is function of time PLO. So now you can substitute in this equation. IP square would be 4 RD square PS average, or which is what I mean by Pn is the same as PS here. So this is also equivalent to RD square PS average divided by 2Q RD delta F. So this is 4 RD square PS PLO divided by, and what is the short noise in this case? It will be twice Q RD. And what is the input power? Input power is PS plus PLO. And since local oscillator power is already larger than the signal power, this will always be only local oscillator power. This is because PS, actually Pn is equal to PS plus PLO, but PS is much smaller than PLO. So what you do is this becomes twice Q RD PLO times delta F. with this information, you can find out what is the ratio of SNR for direct detection for Homodyne and Heterodyne. The second question was for Heterodyne, the first question was for Homodyne. The difference will be in Heterodyne, as I said earlier, you will not really have this 2 because you will when you average out the power, the cos square function would average out to half. So essentially the power in case of Heterodyne, the power will be, the photocurrent will be just RD root of PS PLO. So with this inputs, you can calculate what is the SNR for ratio of SNR for direct detection to heterodyne detection. The question, next question is, let's see what's the next question. Okay, so there is some information given for a Homodyne receiver. So let's see what that is. So the information is coherent receiver in order to get a coherent receiver to the fullest benefit, power of the LO should be high such that the short noise must be greater than the thermal noise. That is a fact that we have discussed in class. The question is, what is the LO power required for so that the LO induced short noise is 10 times the thermal noise at room temperature. So all what you're demanding is sigma short noise square is equal to 10 times sigma thermal noise square at room temperature, right? So sigma short noise square, you know the formula. This will be a function of dependent on PLO, assuming that PS is much smaller than PLO, whereas this would be independent of power. So you can actually substitute, it's a simple formula calculation. We can write out what is the short noise power, which is 2Q times photocurrent. IP is the photocurrent. 2Q times IP times delta F. This is the power spectral density multiplied by the bandwidth. And IP, of course, is RD times PLO. And thermal noise, here you know the thermal noise variance, which is 4 kT by load resistance delta F. So you can substitute here and find out what is the power required so that this condition is satisfied. So that is the next question. The subsequent question is, consider so this is question 3 now. Consider a coherent homodyne receiver. So it is already given to be homodyne receiver with a 13 dBm phase locked local oscillator. So the phase locking is done. There's no omega IF and so on. The local oscillator power is equal to 13 dBm. In terms of milliwatt, this is 20 milliwatt because 10 dBm is 10 milliwatt. 13 is double of that, so 20 milliwatt. Direct detection receiver. Both the receivers use for pin diodes with responsivity and have negligible dark current at room temperature. Detectors are designed to operate 1550. Electrical bandwidth is 40 gigahertz. There's something called both cases. There's no both cases. There's only one detector that is present here. So there's no both cases. There's only one detector. So the detector is operated at 1550 nanometer. The electrical bandwidth is 40 gigahertz. And load resistance RL is equal to 50 ohms. That is also given. It is a receiver of pin receiver of responsivity 0.75 ampere per watt. So this information is given. Question first part is, what is the input signal to achieve electrical SNR of 20 dB direct detection receiver and coherent receiver? Oh, okay. So there is consider a coherent Homodyne receiver with a phase lock local oscillator and a direct detection receiver. So we are considering two receivers. One is a direct detection receiver and the other is a coherent receiver. So coherent receiver has the local oscillator, direct detection receiver does not have a local oscillator. So in the direct detection receiver, I've already told you how to calculate SNR. SNR, if it is not mentioned, it is in decibel scale. Okay, so typically even in class I have used SNR without mentioning the unit. If the unit is not mentioned, it means that it is in decibels. So SNR is again RD P average power input square. This is the electrical power at the input divided by sigma square, sigma S square plus sigma T square, where sigma S square and sigma T square are the variances of the short noise and the thermal noise. So the first part is, what is the signal power required to achieve an electrical SNR of 20 dB? So when you're substituting, be careful. 20 dB corresponds to, in the decibel scale, would correspond to, is equivalent to 100. So SNR is 100 is equal to RD square P in square divided by sigma S square, which will also have a P in, okay, plus sigma T square. So the question is, if you want this number to be 100, what should be the signal power? What is the signal power? So do we have all the data? We have RD, we have 4 kT by R delta F, we know delta F, right? And sigma S square is 2Q divided by, so we have sigma S square is, the short noise is 2Q times I plus ID delta F. Ignore the dark current, so it is just 2Q times delta F. You know all these values, so you can find out what is the power, is a substitution and finding out what is the power required. What is interesting is you have to also calculate this for, this is for direct detection receiver, and the second one is for coherent receiver. Now, do you consider Homodyne or Heterodyne? It's already given, it is Homodyne. And for Homodyne receiver, we have also calculated what is the SNR. SNR for a Homodyne case is here, right? IP square, IP is this. So SNR is actually, this is signal power divided by noise power, but then you should also add sigma T square if there is thermal noise. In the previous problem, there was no thermal noise, so we had not added, but in this problem, we will add the thermal noise, and then you calculate what the power is. SNR is again given to you 100. So that's simple enough. The next question is, find the signal power for which the SNR given by coherent is greater than SNR given by direct detection, right? So this is again extremely simple to calculate, because all what you need to do is to demand that the SNR for the coherent is, substitute the SNR for coherent, substitute the SNR for direct detection receiver, and find out at what power does it happen. So SNR for, again, I'll just write it. SNR for coherent receiver is, the signal current is 2 times square root of PS PLO. And this is Homodyne, so this is just 2 times square root of PS PLO, and you have the RD. So here is the, that's what we discussed in the beginning. 2 times RD root of PS PLO is the signal of interest. That square, because SNR is current square, divided by short noise square plus thermal noise square. This must be greater than, for a direct detection receiver, it is just RD times PS, average PS square divided by sigma short square plus sigma thermal square. Right? Now, You could ignore thermal noise because you're looking at short noise limit, right? Because you know that coherent detection will be beneficial over direct detection only because you're operating in the short noise limit. So for that reason, you can actually ignore this sigma t square, and you can actually substitute this short noise variance, and short noise variance is 2q times rd times PS plus PLO in this case, and in this case it is just 2q times RD times PS in this case. So substituting, you can find out what is the power for which, what is the PS for which, what is the PS for which this condition is satisfied. And you will end up getting a quadratic equation or probably an equation in PS, and you will realize that only when PS is at least equal to PLO, or when PLO is at least equal to PS, you will get both as equal SNR, and that is to be intuitively expected. Okay, so PLO is given to you as 13 dBm. So only when the input signal power comes to almost the power level of equal to the local oscillator power, only then you will have identical SNRs. So that completes this assignment. Okay, let's see the chat window. Yes, Michael Jordan, I was wondering where you are. Don't we need to add any phase noise term in the coherent receiver calculation? Very interesting question. You do not need to add phase noise term because what we are calculating is electrical SNR. Now, electrical SNR is simply signal power divided by noise power. Now, how do you represent phase noise? You say that I have an electric field e power j omega t plus phi of t. This phi of t is what represents your phase noise. But what happens is this electric field of the corresponding to the light wave gets converted into optical power. So the optical power, which is signal power, right? It's proportional to mod E square. And the moment you say it is mod E square, you have lost the phase. So the SNR, you will not see phase noise getting included in the SNR. You will always see only the amplitude fluctuations that gets included in SNR. Phase noise is counted in terms of phase error variance or the line width of the laser. Now, the phase noise becomes critical when you're doing coherent detection. So we have another week for design of coherent receivers. So at that time, we will see how to take care or worry about this phase noise. As I said in the beginning of today's class, we are dealing only with NRZ OK here today. So we are not really looking at phase noise. Okay, any other questions? So the assignment is over. I don't have any other questions. In that case, I will close the session after waiting for 5 minutes for any more questions. Do let me know if you have any more questions. I'll stay online for some more time. Let me look at the forum. So what is happening in the video 000001? Okay, let me check what is happening, which video the person is referring to. Actually, what he has referred to is the beginning of the video, so I really don't know the question. There's another question. I'm not able to access the practice solution of lecture 3, segment 2. So I can check that. That the NPTEL team can check and get back. There's a question on assignment 6. How did you get delta lambda is equal to 0.158 nanometer for 10 gigahertz NRZ system at 1540 nanometer? Okay, so this I think I explained in my previous lecture also. So you start with C is equal to nu lambda. So nu is equal to C over lambda. So delta nu is equal to modulus of this C over lambda square delta lambda. So for 10 gigahertz NRZ system, this is how the spectrum looks like. You will have first null at 10, the other null at omega c plus 10, and the second null at omega c minus 10. So the spectral content is 20 gigahertz. So you know 20 gigahertz is your spectral content. So delta lambda is nothing but lambda square delta nu divided by c. So delta nu is known, lambda is known. C, of course, you know it is 3 into 10 power 8. Substitute this, you will get delta lambda. Is there a chance to extend the assignment date? Sorry, this is not in my control. NPTEL stream controls this, so not possible. There's a question about what I'm doing overwriting. I think that's already explained. Yeah, so there are no more queries in the forum. If there are any more questions for me, please type in your chat window. During classroom exam, any type of scientific calculator would be given or not? Actually, I'm not sure. This, the course requires calculator, so I think you will be able to access the computer calculator, which is a scientific calculator. So I think that's possible. Are there any other questions? Be happy to take. If not, can close the session. Mahesh, there are no more questions, so we will close the session. Yeah, thank you very much. Yeah. Next week is going to be very tough because the assignments are really long and the content is also slightly longer than the previous week. So please start preparing on time.